Hey, welcome everyone. We're very happy to have Nima Lashkari, and he's going to go through Spacetime Symmetry from Modular case.
Thank you so much for the invitation. It's a pleasure to be back here after a couple of years. So today I'll be talking about emergent spacetime symmetries from modular chaos with an asterisk. That means that I will intentionally not define chaos, but I will define whatever I use. So this is a word that is perhaps a little bit imprecise for the context of our conversation today, but I'll be very precise about what I'll be talking about. So this is working collaboration with Keiichiro Furuya. I'll just say my former student, then Quinn Leon, current student, Modeste Musa, former postdoc, and Shoei Youssef, former student, all at Purdue. So these are some references. And then there will be a paper coming up that is taking a little bit longer than expected, but it will come out soon. All right. Please stop me at any point, right? So in terms of motivation, I'll try to start with two different sets of discussions. First motivation is holographic, right? So the idea is we've learned a lot about the emergence of space from entanglement, or the connection between space and entanglement. That started with Ryuta Karnagi from 2006, then Mark von Ramsdong pitched this idea. Well, I might not be very precise about who I'm referencing. It was not just Mark, it was a lot of people. So I apologize in advance because it's being recorded. But correlations or entanglement is a measure of proper distance, right? Distance between two regions. For example, if you have a wormhole, you have a subregion here, then the amount of mutual information which between these two regions is a measure of the proper distance. As you pull these guys apart, the mutual information drops and the proper distance increases. This kind of activity led to a lot of
proper distance in what metric?
Oh, this is just very rough.
Oh,
It's very, very rough. Then it led to more activities regarding that go.
But if you computed a 2-point function across, then that would really be geodesic.
yeah.
For massive, very heavy process. And then there was a connection between quantum error correction and bulk reconstruction and a lot of other developments. Then that led to the development of holographic tensor networks, which was trying to give a more intuitive picture, thinking about how space is encoded in entanglement. But I want to just point out that in a lot of these developments, it's about reconstructing space, and an ingredient that's kind of mysteriously left out in some of these discussions is space-time, right? For example, if you try to take this picture of tensor networks that we love and use all the time to get intuition about holography, that picture and the bulk time don't quite come in piece together. Like, so that picture does not quite teach you much about time, the bulk time, right? So there is a question of the bulk time. But this is motivational, right? So a lot of what I should say, as was started, at least from my point of view, by some work by Hong Liu and Luthazer, and more people at MIT, and some other important work that actually predates that by Lamprou, Yan Degor, and other people. All right. So to be a little bit more precise, here's what I'm going to say. There are many vacuum and quantum gravity where lots of different states are represented by the same geometry, smooth Lorentzian geometry, right? So for example, imagine some sort of a ADS-CFD setup. There is an eternal black hole in the bulk, or some sort of bifurcate killing horizon. So this is smooth space-time that's coming out. And the fact that I say smooth space-time means that locally around each point, there is, at least in this picture, I'm drawing a local Poincare, two-dimensional Poincare algebra, right? That is generated by these translations here, I'm gonna call G plus and G minus. And the local boost around here. So there's this algebra, which G plus and G minus almost commute in some order, in some limit where you zoom in near this region. And also, if this is boost, G plus minus and B are like 2 pi, well, let's say plus minus I, G plus. Alright. So this is a local two-dimensional Poincare group, right? And of course, you could zoom in here and see a flat space, boost, null translation. Then these two directions correspond to growing and decaying, exponentially growing and exponentially decaying nodes. And there's a coefficient of 2 pi or 1 in this convention that is important for the Lie algebraic structure. Right? Good. So the question, first motivation is that how is this? So the fact that universally a lot of these universally this kind of smooth Lorentzian spacetime comes out means that there has to exist a local Poincare group algebra, that or approximate local Poincare algebra reflected on the boundary algebras. Somehow it has to be there. So we will be after that. We'll be looking for that. Another thing to be said right away is that there, so that's local 2D Poincare. There's also, every time you have these bifurcate killing horizons, you also have a PSL2R on the future horizon that acts on the future horizon, and a PSL2R that acts on the past horizon. These are conformal symmetries, right? That acts on these on the horizon generators, and those also have to be reflected somehow in the boundary. So this part of it is going to be about deriving or characterizing the necessary and sufficient, sufficient condition for these to emerge out of the boundary.
So should we expect this whatever local Lorentz algebra only if the curvature length scale is large and strenuous?
Yeah. So I will actually take that regime, and what is really interesting is that today I don't have any story to tell about how the curvature, which is the next order corrections, encoded on the boundary, but that's less universal, of course.
So it's like in a strong coupling, large lambda limit.
I don't want to say that for now.
Okay.
Yeah. I'm not sure if it is strong coupling regime, but we'll see.
Okay.
That's actually important.
Yeah,
What?
large gap maybe.
Well, let's get there. I don't wanna say it's large gap.
Okay.
So-
When you say PSL to us, what's which generator referring to?
So there's like a component group that on this horizon, you have let's say conformal, we'll have a conformal field theory living here, like chiral modes. And there's the action of the PSL2R in the beginnings.
Is we're working in some particular dimension.
Yeah, I'm looking at the S wave. Right, I'm just looking at the S wave. So this is the eternal black hole, at every point there's some sort of sphere. I'm just looking at the S wave. It's actually very important for what I say that I focus on the S wave.
Right, just to be totally clear, if we're n equals 4 angles and lambda is 0.1, do you expect this?
One of the interesting open questions at the end of the talk would be that I'm not sure. I think, well, it's possible. It's possible that n equal 4 super angles for finite values of lambda shows this behavior I was talking about.
Right.
This is still it's a possibility.
Would be unexpected, right?
It will be very unexpected.
Okay.
But that's actually one of the important things that I would say that it's an important open problem.
What's probably unexpected is that it's realized locally in the park, right?
So, yeah, that is, well, okay. Well,
I didn't understand. Why should it be there at all?
Well, I don't know, but I'm saying that at strong coupling, when there's a smooth spacetime in the bulk, we would expect that it's realized locally. Now, it could be that it's realized non-locally, there's some crazy.
This is the take home lesson on it. It's surprising that it's there. And we will have to check it whether it's there, but
But that's a miracle. There's no reason to expect that.
there's no, at this point, no. At this point of the talk, no. So you're getting to my conclusion, there's a surprise, right? So that's motivation number one is this. Motivation number two, actually going along the lines that Charles was pointing out, is not holographic, or at least at the moment. This motivation is along these lines that every time we have a local quantum system, the geometry is encoded, let me say it in words and I'm going to explain, in a net of algebras, operator algebras. So for example, here is some sort of space-time diagram. In quantum field theory, to every open set A, we associate an algebra. And this map will have nice properties. It preserves inclusions. If A is inside B, then the corresponding algebras will preserve the structure of inclusions. And at this point, we call this a net of algebras. Okay, sorry. A net of algebras. Now, there's no geometry at this point yet, but the geometry is encoded, or partly encoded in this net of algebras in the following way. If your space, your manifold has a bunch of symmetries, so the symmetries of this geometry are going to be encoded as symmetries of a net of this net, the net of algebra. Okay. So for example, if this is flat space on quantum field theory, it means that you have the Poincare group. Poincare group sends these regions to each other. It's an automorphism of these open sets, and correspondingly the algebras move, right? So if a particular transformation sends A to alpha G of A, right? The algebra correspondingly is moving with it. So it's covariant. It acts covariantly. And the fact that we say it's a symmetry realized on the net, it means that on the Hilbert space, these are represented by a unitary group, right?
The symmetries, are you including them in the algebra also? Or this is just local algebra?
No, these are just local algebras. They have to transform under these symmetries. The symmetry means that there's a unitary group that acts on the Hilbert space. Yeah. So, all right, so this is good. Now, part of this story is, can you go the other way around? Under what conditions can you go the other way around? If I give you a net of algebras, right? And I tell you about a bunch of nice properties that it have, can you see a geometry in it? Right? So this is intimately tied to problems of nature quantum gravity. If I give you sorry, 1 second, non-commutative Van Neumann algebra, under what conditions do I start seeing something that looks like geometry? So here, it's a little bit like what Shiraz was saying earlier. We're gonna see that under some general conditions that I'm not sure large gap is required to satisfy those conditions, there will be these symmetries, PSL2R like or local Poincare algebra that will emerge. Now, it's unknown at the moment. We're trying to look into it, but we're not quite sure if you need some other holography gives you examples, but this might go beyond holography.
So the way you motivated this arrow was to consider symmetries of the conformity, right? The boundary, some quantum system, symmetry of the quantum system.
Some quantum system, some abstract methodology.
So now when you're asking this question backwards, you are looking for the symmetries which are not even there. Quantum system, some in some way they're present, but not quite. I
want an abstract characterization.
Okay.
Of some criteria, some abstract operator algebraic criterion that will tell me, guarantee these symmetries. It's a program that, so now, of course, I'm relying on a lot of these results that algebraic quantum field theories developed. They didn't have this picture in mind. They're mathematicians, they want to make sure that when they talk about operator algebras, everything is written in terms of operator algebras. They didn't want to assume much. So a lot of these results have origins there. But from the point of view of, so of course, this looks like quantum gravity. seeing geometry.
But you're, when you want to go towards the bulk, right, from here you want to get a handle on the bulk, right?
Yeah.
So there, I mean, so what sort of operations in the bulk correspond to symmetries?
Very good. So the talk is going to be about this. All right. So two pieces of motivation. One holographic. This, right? How do you characterize in these holographic theories these symmetries? How are they characterized on the boundary? And the answer is going to be in the chaotic or ergodic properties of modular flows, right? And here it becomes like this. If you have a bunch of an abstract net of algebras, there are these modular flows. You could ask about whether these modular flows are chaotic or ergodic enough. Every time they are enough ergodic or chaotic, this structure emerges. Now, what is interesting is that we see to satisfy these requirements, we see the necessity, at least at the moment, of large N. But large gap at the moment doesn't seem to play a role. We need to investigate this further. Yeah.
Is it a unique structure which we will get this side from the algebra?
Well, I'll write theorems. So, like I'll write specific theorems. That's why I specialize to PSL2R and local Poincare algebra. But there's a bigger picture that we're trying to work towards, which is, okay, it's being recorded. Let me just say this. I think this line of thinking, just if you push it to the limit, the kind of theorems that we're proving now, push it to the limit, what you're going to reconstruct is the Penrose diagram, the conformal structure. Now, reconstructing something like curvature is more nuanced. Yeah.
So if I start with the quantum theory on a lattice, this is all going to be.
It's one of my examples. One of my examples is lattices, and I'll make a comparison. Very good.
So at least in this OTOC calculations,
Mhm.
there was a relationship between maximal chaos and strong coupling, right?
Yes.
But that is not going to play a role.
This is not that maximal chaos. That's why the asterisk. This chaos, if you want to call it chaos, one can say it's always maximal.
I see.
Now, there's a beautiful interplay between the two, but yeah.
What do you mean by large gap?
Oh, well, at this point, let's ignore all of those comments for now, right? I said what I said. If I have a local quantum system, it gives me a net of algebras, and the symmetries are reflected in the net. Now I'm just going to abstractly ask about the criterion algebraically that I need to see this geometry. Let's forget about large gap or anything like that. All right. Out of the way, let me try to explain this a little bit more. There was a question about lattice, so I just want to explain that a little bit more. I think, at least for me, it's helpful to, I wrote local quantum system. So the example I want you to have in mind is something like a set, a spin system, right? A bunch of spins sitting on vertices of some sort of a lattice. I'm going to call that X. Of course, for every set A, I have this map, right? And it has this nice property that if A is inside B, then A is inside A of B. But a priori, there's no clear geometry here, right? For example, is this one-dimensional? Is this two-dimensional? To see anything like that, if I want to argue that this is, for example, at least one-dimensional, let's say this is an infinite system, I should find some sort of a translation, discrete translation operator here, that first of all, it leaves my vacuum state invariant. Let's ignore that for a second. But the structure that we're going to be after is what I'm going to call half-sided inclusions. It's very intuitive. If you have a 1D system, you have this algebra R to the right, such that for all positive values of translations, this is sent to stop algebras, right? For all x larger than 0, the translation as of this right algebra is inside R. Right? This is one key physical operator algebraic characterization that I want to point out, right? Every time I see a structure like this, it smells like one dimension, right? Now, if I had a system that if I could organize my degrees of freedom this way as well, right? And then I had another one, e to the power of I p y a, that does translation like that. And on top of it, if the generator commute, then I would say it looks like I have R2. But the structure I want to point out is these half-sided inclusions. Now, this is just heuristics, okay? There's no theorem at this point. So every time you hear half-sided inclusion and why it has to do, that's the structure that is seen or observed here to deduce some sort of geometric.
But if you take scale, for example, scaling inside, that's also satisfies that. But it's not
Very good. So an example, yes, well, scaling this will not set. So think of a tensor network setup like Nira. Right, you put the degrees of freedom like this. Now you could try to find PSL2R here. Of course, discrete versions. I didn't give that example because dilatation is hard to discretize. Right, makes you laugh. But this is a discrete PSL, well, something that looks like, smells like PSL2R on the upper half plane for these systems. All right. So the structure I want to point out is that if I have my system X, isometries that we're talking about span X to X, right? And they're going to be the symmetries of the algebra. So if they span A, so if this is the map, and then under alpha, this goes alpha of A, then A of alpha of A, the alpha you like this, and then I say the word symmetry. Here you might ask, like, what is the Hamiltonian? What is commuting with what? Ignore all of that. All that it matters for me from when I say symmetry, all I mean is the action of a Lie algebra, Lie group in this context, such that I have a state that's left invariant for all operators A. Well, let me call it X in my big algebra, the state is invariant. That's all I mean by symmetry, just to clarify. Right?
In QFT, we at least mean that we at least want that it's sort of locally, like there's a stress tensor. There's a spacetime symmetry generated.
It's not always local generated. GFF is an example. General restrictions.
So you don't even want that it's local.
I don't need to. Well, I mean, I can say more words, right? But if I can get things done without saying them, right? Okay.
So Nima, does gauge
Yes.
symmetry complicate your story?
Sorry,
Gauge symmetry.
that's not symmetry.
Well, what a gauge invariance.
Redundancies, right?
Yeah, redundant. Does it complicate your story or it goes through? Because this lattice picture kind of is a little tricky, right? Bonds and so on.
I don't have anything intelligent to say about that for the following reason that in the structure, well, I didn't say some. So if you look at the way I put it, so if you look at here, it looked like I'm writing down the axioms of local quantum field theory. I intentionally hiding one, which is causality. It says that if you have A and B are two regions that are causally disjoint, then the corresponding algebras commute. You take this to the extreme. In this case, it tells you that there's a tensor product structure, so you don't have non-local, genuinely non-local operators that are not generated locally. So this is related to the violation of Hart duality. So there's a story over there, but I think my discussion is a lot more basic. So it's imaginable that there's a more nuanced version of this that would apply. So the terminology of gauge theory here is about violation of Hart duality. Hart duality is the following statement. One of the operations you have here is complement. If you have a set A, you can take the complement of set to get A prime. Now the question is does this map commute with that, right? Is it true that A of A prime is the same thing as A of A commutant? If that's true, that's called Hog's duality, and this is what's violated in gauge theories or global theories of global symmetry as well.
You'll be using Hugger.
I will not be using Hog's duality.
Okay, so it goes through that.
In the two theorems I mentioned, we'll go through. There's a catch. There's a place I give examples or Hog's duality. Anyway, I'll talk.
Sorry, A is a region on the boundary?
A in this language is a subalgebra. Yes, say.
And curly A is the algebra associated with that region?
Yeah.
But I thought we were interested in sort of finding algebras with the regions in the bulk.
So this think of it as a abstract label index.
So it's not thought of as a parameterized by a region on the boundary.
Not necessarily.
So why do we have it's just something.
Just because but these nets of algebras, and they're super abstract. Right? I just have some labeling.
So algebra means closed under multiplication and addition.
These are C-star algebras, so there's also star operation.
Star operations for coefficient conjugate.
Yeah, yes. But so there's an involution, something that doubles to itself. Yeah.
Okay.
These are also normed algebras, so they're bounded operators. All right. Good. Any other questions at this point?
Your intuitive statement so far about the half-sided modular inclusions is that if you have some number of half-sided modular inclusions, that means you have the same number of dimensions.
So in this example, it's not modular. It was not modular. I just said half-sided algebras. And I'll actually point out the distinction, the difference between this example and modular inclusions. I'll point out, well, if I can say it quickly. In this case of half-sided algebras I gave, the generator is not a positive operator. So it's about growing a space dimension. Now, half-sided modular inclusions are about space-time. They have to do with time. And for that to come in, it's important. It's absolutely essential that the generator of this unitary group is a positive operator. But that's just something you have.
But so far the statement, if you have these half-sided inclusions, then that gives you some information about the number of dimensions in space.
Heuristics. There's no theorem over there. It's very hard to make progress over there. It's just motivational, right? I'll get to my theorems. As you can tell, of course, I don't have any theorems if we're talking C-star algebras. I have to have one Neyman algebras to have theorems. C-star algebras are very, very broad.
So maybe Shreya would like you to see the S5 as well.
Right.
Shreya would like you to see also the S5.
S5.
Not just the ABS5.
Oh. Well, okay, so that's a lot more.
That would be very interesting.
Yes. Yeah, unfortunately, I would love to, I wish I had examples to make this less abstract. We're working on the example, and the example that we're working on is not n=4 superangular finer coupling. It's actually SYK in different regimes that are not holographic, large Q SYK. This is simpler to work with. All right, but we think the structure PSL2 and all that I'm talking about is there. Large N is essential, but those spheres, at least in the regime of SYK, the SYK symbol doesn't have the large N.
So Nima, this inclusion business, if the dimension that you are interested in is compact, circular, then what will that be replaced by?
I do not know. This was intuition mostly coming from these non-compact Lie groups. And I do not know.
Because we don't expect the physics to be any different if we have a huge circle or a non-compact space, right? So that should be visible from that algebraic point of view also.
No, from the algebraic point of view, it's not visible. The two theories are distinct because we're talking about, as you'll see, we're talking about processes, modular ergodic properties of subalgebras. Now, if it's infinite, it's possible for things to decay forever under modular flow, whereas if they're finite but large, there will be Poincare comebacks. And these theorems crucially rely on some regime limit where things just decay. Strong mixing in black holes, information loss in black holes, for example, right? The 2-point function just decays forever. And that's an artifact of large N. That's why I sort of need to take a large N limit. All right. Okay, now let's say things that are a little bit more concrete, but work towards things that are more concrete. But before that, let me just say the message. Chaotic / ergodic properties of modular flow sometimes encodes or tells us about the emergence of a smooth Lorentzian geometry. That's a message. Now, as we said a couple of times, the surprise is that these criteria seem to be satisfied in theories like SYK that have large N, but not necessarily large gap. So the question is, what is this geometry? What are these BSL2Rs we're talking about? If they're present, they're probably not, they're not local space-time. What are they? Okay. So what are their results? There are two results I'll quote. One is that, well, actually, yeah, I'll put two for now. There's an emergent local, quote unquote, I'll explain what it means, 2D Poincare algebra, every time we have in any quantum system, with the following property, something that I'll call future / past modular algebras. So this first statement, that this is an informal statement of a theorem that I'll explain. Two is that same thing, if you have a future or past modular algebra that is standard, then you instantly get a PSL2R. So I'll explain what standards are. So my next point will be to explain what future past modular algebras are and what are standard. What's the definition of standard? Right? And these criteria seem to be satisfied, at least in some theories, that we perhaps don't expect them to be holographic. Right? So in this example of a 1D chain, I can explain immediately what just choice of terminology, what is a future algebra. So this is, I'm gonna call this, with respect to translation this way, I'm gonna call this a Reich algebra. I'm gonna call same structure, future algebra, if the generator of this is positive. Now, if I want to give you a little bit more of a definition, let me say the words first. If the set of all measurements I can do from now until eternity forms a proper subalgebra of observables, I call that future subalgebra. Proper subalgebra, right? Because in the generic quantum system, finite dimensional, of course, that will be the whole thing. So there is these inclusions I'm talking about are trivial. So there's nothing to read, right? So when does that happen? Let me give you some examples. So let me should I write it? Yeah. So future, I'll draw pictures instead of writing it. So let me repeat, if the set of all observables I can measure from now until eternity forms the algebra, that's proper subalgebra, then it's a future subalgebra. Example, so let me give a bunch of examples. Take flat space on quantum field theory. This is the Penrose diagram. The set of all observables here forms a future algebra. The form of the set of all observables here forms a past algebra. These are von Neumann algebras, meaning that they're equal to their double commutant, if I can localize things out here. Because imagine this is the algebra. What is this commutant? It better be here and here, right? If I cannot localize anything here and here, for example, in massive theories, the commutant is going to be trivial. By taking the double commutant, I get the whole thing. So I do not, in massive quantum field theory, I do not have a future von Neumann algebra. For me, that's very important. So even though every time I say the word modular, I mean von Neumann algebras, because modular flows are defined over there, right? So if in conformal field theory, for instance, that's one setup where you get them. By massive field theories, you do not obtain future von Neumann algebras, you have future C-star algebras.
So what is a double commutant?
The commutant of commutant.
So sorry, just to be clear, just so that I understand. If I take a Cauchy surface that sort of hugs the past light cone here. No, sorry, future light. Okay, fine. Yeah, if I take a Cauchy surface that does this, this, and this, all the data here is the commutant of this. I see.
But if I have there is data here, if I have a CFT, if I have massless theories, if it's massive, there's nothing, right? So the commutant is identity. If I further take another commutant, I get the whole thing. This is actually a theorem that was proved, I'm just providing the intuition for it, but it was proven back in the 60s very abstractly by algebraic quantum field theorists. So this is example number one. So yeah.
By proper subalgebra, we mean subalgebra which is on one line.
No, proper subalgebra means that it's not equal to the whole thing.
Oh.
Yeah. This picture, think of it as like sitting at a point and shooting a null ray towards the peak.
So in the case of massive quantum field theories, just that F diamond is everything.
Yes. Yeah. But as a F is C-star algebra, and if you want to, you have to take the double commutant, enlarge it to get a von Neumann algebra. If you do that, you get the whole thing. So it's trivial.
Sorry, so what makes it future? That's because what?
It's just because it's all observable to the future of a point.
Okay.
Right. And so the half-sided translations are just Hamiltonian evolution. For all values of positive time evolution is restriction. That smells like second law of thermodynamics, by the way. Which is not surprising.
So this is again kind of an inclusion, so you can have a future inside future.
This is to be compared with this example of half-sided inclusion I gave, right?
Okay.
This is to be compared with that example. But it's essential here that time, the generator is positive. The only thing that goes into a theorem that will not apply here is that the generator of this guy is positive.
Because it's like time translation.
Yeah.
Wait, can you explain your remark about the second law of thermodynamics?
Well, the second law of thermodynamics is the following. You want a function that is monotonic under time evolution, right? And it's a measure of the amount of entropy in the system, right? Imagine this is your future algebra. This is everything you could observe from now until eternity. And time, of course, shrinks that. Now, if you have an entropic measure of how much information there is in this algebra, of course, that instantly gives you a monotone, something that decreases monotonically under time. Well, sorry, increases monotonically under time. Let me give you a particular example. If I take this subalgebra and something outside it, for example, this, take the mutual information of them. That is a monotone in time, FMD. Why? Because by data processing inequality, time evolution is restriction, strong subjectivities or data processing tells you that this monotonically decreases. So, okay, you might have more requirements for entropy of the second law, but at least it's a monotone.
There's a second law associated with an observer.
Correct. Correct. Yeah. Now,
this does not use positivity, right?
This
does not use positivity.
of the generator.
Of the generator.
It does.
It does?
It does.
It
Oh, sorry.
Inclusions.
The proof that the mutual information will monotonically decrease, of course, is the use. But like to interpret this as something like second law, you need to have dynamical process.
Okay.
Yeah. Okay, example number 2. If we have a theory that violates the time slice axiom. What is the time slice axiom? Time slice axiom tells you that, well, classical time slice axiom tells you that if you have the information of the field and its derivatives at a particular time slice, you could evolve this towards the future. The quantum version of that is that if you give me the correlation function in a thin, arbitrarily thin region, I can evolve these guys forward, which means that this information content is the whole thing. Now, if for some reason time slice axiom fails, as I go to the future, I need new data, right? Then it's plausible that there is an algebra associated to the future of this point. Like these could be realized explicitly in large models like generalized free fields, as was pointed out by Leo and Luthausser.
So like the exterior of a black brane, single trace operators in the exterior of a black brane. Yes.
In the strict and going to infinite limit.
Yeah.
Because otherwise they won't close.
Yeah.
From an algebra. Right.
This requirement that you need to know correlation functions in this thickness time slice. I mean, it would be enough to have them in some small ball, right? Using analyticity, you can control them and give it. Why do you need this kind of thing?
You might be right actually about that, because yeah, the time slice axiom is usually formulated this way, but using Riech-Leiter, you could just relatively continue. Yeah. Because yeah, that's correct. That's correct. But I mean, Riech-Leiter is a specific thing to something that's specialized, specific to like relativistic theories, but this could be defined for anything. For quantum mechanics or anything.
So how does that work in exterior of black brane? We could have new data.
You're using some gravity or?
Just take the exterior of a black brane, or even a black hole. Even any pure n equals 4, even pure n equals 4 angles. You need the data on the boundary over a strip of pi or 2 pi in order to be able to evolve the future.
Yes.
How does your
I mean, this is the correlation functions are analytic, and once you know them in some open interval, you should be able to analytically conclude them.
yeah? I'm trying to
Yeah. But in n equals 4, I mean, I don't know about how to think about it with the black hole case, but the last thing that you said.
Let's just do vacuum.
Yeah.
Vacuum. It depends on the state. You could have at one time slice, you've got something in the middle that you cannot yet see on the boundary, and that will hit you at some point.
Yeah, it might be related to infinite n versus finite n. Right, when you take into infinity, these analyticity properties fall apart. Right.
Were you talking about it in the vacuum? Was it analytic in the vacuum? It's very important for what I'm saying that it's not the vacuum.
The Riech-Leiter theorem will be applied to the vacuum state.
Sorry.
There are versions of Riech-Leiter, yeah.
Does it apply also to states which locally look like the vacuum?
Okay, that I don't know, but it applies, the Riech-Leiter applies in a dense set of states.
There should be states where I can violate, right? Because I can do something here
100%.
and not do something there.
No, 100%. But yeah, there are definitely states that is violated, for sure.
So this must then be.
Yeah.
Okay, he wants this for all states, right?
So example number 3 is chiral fermions or chiral field theory in 1 plus 1.
Just one question. So even with this line band, how would your objection?
Yeah. So I here this would be an example where a time band is not enough. If I increase the time band, I will get more until I increase it to 2 pi or pi. In the case of a black hole, I think you have to increase it forever. I mean, no matter how much you increase it, you will keep getting new data. Because then the data hugs the horizon. That only comes at very late future.
Yeah.
Yeah, of course, infinite n equals 4.
Yeah, then there's
one slice and that's it.
Yeah.
But in this, you're keeping track only of single trace.
Yeah.
It's a funny thing, right?
For sure.
Okay.
So this example of chiral fermions, for example, is something going between the lattice, it's like a right translations. But because the system is on a null surface, P minus, or the generator of this translation is positive. So it's a happy medium in between the two examples, right? So these were this was time evolution, space evolution, of course, is not positive generator. Here is null evolution, the generator is positive. All right, and then the last example I give is the example that I will use a lot. So in the examples here I gave, none of these flows were none of the dynamical evolutions were modular flows. My theorems, or these theorems are powerful if your flows are modular. Now take eternal black hole or any black hole that's has a bifurcate Killing horizon. So because it has a bifurcate Killing horizon, if this is U and this is V, then you can prove that this is the modular flow. U del U minus V del V is the modular flow. And this is the future algebra, modular future algebra. This is the modular past algebra. Good. All right. So any questions about what the modular future or modular past algebra is?
I'll really embarrass myself.
Yeah.
What do you mean by modular? What is a modular?
Modular flow.
What
So
is
the dynamics, what is modular flow? It's if you have a density matrix, bro.
Okay, so the Hamiltonian of that is dead.
Exactly. Log of the, yes, correct. It's
In this case, this is the Ringler, the Ringler time. So these are.
it looks like, yeah, it is a black hole.
Close to the horizon.
It's a killing flow.
Yes, okay.
Yeah, it's a killing flow.
And this modular flow is always positive.
No, that's very, very good point. The generator modular flow, for example, in Ringler space is boost. It's not positive. So what is this positive operator I'm talking about? There's a theorem that this half-sided modular inclusion. It tells you that every time you have one of these positive generators, you can construct modular flow, future modular algebras, and every time you have future modular algebras, you construct these positive operators. What are the positive operators? If take an inclusion, so here the future algebra is inside the right wedge. The modular flow of this, the log of it has a modular the modular Hamiltonian. The difference between these two is positive or negative. And every time you have a positive operator, you could reconstruct this modular inclusion and vice versa. It's kind of a neat setup.
So just to understand this modular flow, so I've got some algebra, I've got some density matrix associated with that algebra.
Right.
Now I use that density matrix to flow that algebra.
Correct.
And that makes it smaller, you're saying. Okay.
All right. Any questions about what a future or past algebra or modular future or modular past
Sorry,
algebra is?
just to, so the modular flow of the bigger algebra makes the action of the modular flow of the bigger algebra makes the smaller algebra even smaller.
Okay, what was the smaller algebra?
So here is the right
Ah.
wedge is the big one, and
The
future.
original algebra is that in there.
Yeah, so
I see. Now I understand. Okay, thank you. Yeah, thanks.
Okay. Now, what is, so that's the setup that I'll be using to get this local Poincare, right? Now, what is standard? Except if you have
There is some more dimension. So the fact that the rho itself is a positive operator doesn't do anything. I mean, it's not.
here, that positive operator is the translation along this. But from this translation, you could construct the modular flows and vice versa.
So why can't I do the inverse modular flow and make the smaller algebra bigger?
Well, then you could.
You could.
I mean,
There's no
these are
concept.
all defined up to plus minus sign.
Okay.
Right, but usually the thing that we usually think about is the future and the past.
Okay.
Right, but it's important that the past. Yeah. Okay, so what is it? Anytime I have one of these future modular algebras, I get the following Lie algebra. T going to AT plus B. It's a Lie algebra, right? It's it's basically translations and boost, right? Boost is this and translation is this.
You said, I'm so sorry,
No worries.
but this translation, I didn't, I get now what you mean by this boost, which is modular flow.
Right.
What was the translation again?
So I will say this explicitly later, but every time you have a setup like this, you have the modular Hamiltonian of the right region, modular Hamiltonian of F. So K of right minus K of F is a positive operator, and you can prove that that precisely that positive operator. And these are equivalent sides of the same thing. These are called half-sided translation. I just didn't want to introduce that terminology. They're the same thing. They're all the same.
So what you constructed is a positive generator which leads to inclusions.
Yes. If the starting point could be you giving me a positive operator that's a symmetry, you leave my state invariant. I instantly know I have these modular future algebras, or we can talk about modular future algebras. But if I want to, in the program that I had, which was characterizing everything just in terms of the algebras, the net of algebras, it's a little bit weird to assume that you have some sort of translation. But modular flows are always well defined. Right?
No, but then how did it give you two-dimensional algebra, A and B?
Oh, it could be viewed as one-dimensional, right? Like just boost and translations.
Boost and translations.
Now, from the boost and translations, I get this AT plus B, right? Well, okay, I'll explain it later.
There's also T minus.
Yeah, that's a past algebra.
So, I see, you don't want to put T plus T minus and boosts together.
No, they won't,
That's not
they won't,
okay, sorry.
because they commute. The generator P plus and P minus
Okay,
commute,
that's right.
flat space, right? So you get two copies of this algebra
I see.
in flat space. But, so cyclic, standard. Now, this is the one that is a little bit harder to explain in words. Yeah.
Sorry.
Yeah.
Now I could play this game for any region on the boundary, right? Computing and time constructing density matrices and so
Yeah,
on,
yeah.
not necessarily half one-sided
Yeah.
in this setup, right?
Absolutely.
So that would assign these kinds of algebras to every local region pretty much on the boundary, right? Every region
Yeah.
in the boundary.
Yeah.
But you expect everything to kind of gel together well to form some consistent bulk picture, right?
I guess so.
And then how does that come out of this kind of thinking?
At the level you're asking, I don't have a sharp answer. We just have a couple of theorems, and it becomes a question of the structure, example by example, we have to discuss, right? If you're talking about SYK at large Q, then we can be very specific. But I don't have the grand vision. But the theorems are theorems, these are forever, right? So the standard inclusion. Now, here it's a little bit tricky, but bear with me. This F is inside R. What are the operators in R that commute with F? They're going to be localized here. This is called a relative commutant. Operators inside the smaller algebra, inside the larger algebra that commutes with the smaller algebra. If I have massive free fields in the bulk, this is going to be empty. In 2 dimensions, there's always a Carl stress tensor, right? So, but in CFDs, there's an algebra here. Now, an inclusion of this type, modular future algebra, is standard if this relative commutant is cyclic, meaning that by acting with the relative commutant in the vacuum, you get everywhere in the Hilbert space. It's a little bit hard to say in simple words, but of course, that's not going to be the case for any theory that has both left movers and right movers, right? Because this null segment. Well, okay, I'll explain that in a little bit.
Just say once again what you meant with the cyclic thing, the relative commutant.
Meaning that, so there's an algebra localized here.
Yes.
This acting on the vacuum
Yes.
gets arbitrarily close to any
The
state.
state is cyclic with respect to the rest. That
Yeah, it's like Riech leader.
Okay.
Is this sub-algebra Riech leader? It's not the right way of saying it.
And if this was a quantum field theory, you would expect the answer would be yes, right?
No, because this has zero volume. The Richter theorem quantum field theory has this finite volume. Now, if these were chiral fields, yes, you'll be absolutely right. And that's actually why I get a PSL to R on the future horizon, and I get a PSL to R on the past horizon. For the modes that are localizable here, in that small Hilbert space, this is cyclic.
And you said if that happens, then what?
I get a full PSL to R. Algebra. And that PSL to R corresponds to the algebra of, there's some sort of conformal group acting on the future horizon. There's one acting on the past horizon. So, questions about the definition of future and past algebra and what the standard is. I understand. I did my best to explain the standard inclusion. I don't have a better intuition. Apologies about that. But that's sort of where we are right. There are more abstract ways of saying it, but I would confuse even more.
And why did you say it's a relative commutant as opposed to just a commutant?
Because this commutant means in the whole Hilbert space.
Okay.
Relative means with respect to this.
Subalgebra, already a subalgebra.
Yeah. Things inside the larger algebra that commute with the subalgebra.
So as you said, if this diagram represented just a flat space CFT, and we were interested only in the left movers,
Yes.
then the answer is yes.
Correct. Yes.
Yeah.
And same theorem, even if it's not flat space, but any black hole with bifurcated horizon, the answer is that there's a PSL to R acting over there and one in the past.
If I
Yes.
ask this in your first example where you had this future algebra in there, and you looked at a relative commutant, which is some part of null infinity, right?
Yes.
So there one would still have a
In a CFT, yes. Yeah, so then there's a PSL to R. What is that PSL to R? It's generated by these null translations, and the modular flow of this, which in a CFT is just dilated. So this was also worked out by the way. Now, here is, for those of you guys who know the literature really, really well, would immediately confront me with the following lie that I said. I said that the modular flow of this region is dilatation. If you go through the proof, it was proven for massless free fields, not for conformal field theory. Now, the theorem that I said, I've been saying PSL to R. Every time this subtlety comes up, CFT versus massless free fields. Massless free fields gives you a representation of PSL to R, action of PSL to R, whereas in a CFT, you get the action of the universal cover of it. Because of the phases that come up as you go push in the Einstein manifold, you push up by 2 pi. So the theorem is applied nicely. I'm just trying to simplify it for the sake of expression. All right, good. Now let me explain this PSL to R business a little bit better, because so far I've just said good words, but I'm not explaining much. All right, so I'm gonna draw this picture. 2 different colors. And I'm gonna give them names. So I'm gonna call this future algebra, I'm gonna call it A plus, and the past algebra is A minus. Okay, and the right wedge is R. So here's the theorem. It says, consider you have these are future and past modular subalgebras. Of course, by definition of modular past or future, you have the following thing. For all positive S, modular flow of S, A plus, let me, is this notation familiar, comfortable? So this I'm going to define A plus minus of S.
R is the whole space.
R is the right wedge.
Yeah.
For which the modular flow is just killing flow. Plus minus S inside A plus minus. So intuitively, and let me define K of R minus log of delta R. Intuitively, you know that if you take this and the future algebra and modular evolve it back a long time back, this algebra gets larger and larger, right? You don't cover this much. So this is the future algebra, but from a long time ago. If you do the same thing to the past, this was very, very large. Now you're sort of zooming in near the horizon. That is the notion of a local or approximate. So it's the scaling limit, where I'm going to explain in a second. You take the future algebra from a long time ago. Long means what? There is a scrambling time. There's a time scale of beta, T over beta, right? That's the dimensionless parameter. So,
Sorry, Nima.
Yeah.
I'm thinking of that operation, this delta, A plus minus delta,
Yes.
is flowing in one direction, let's say to the future. Okay. So then this will take A plus and make it a subset of itself,
Yes,
but it would take A minus and make it a superset of itself, right?
correct.
So then why?
There's a minus sign.
Oh, okay.
So one of them are belong to future, the other one to past.
Yeah.
So now there is this positive operator that you could define as K of R minus K of A plus minus of S. All right. And you could prove it satisfies, so this is a positive operator. It satisfies the following algebra. G plus of S is just plus minus 2 pi G plus minus of S. So far, this is like, if I just find G, this looks like 2D Poincare group algebra if G plus and G minus commute. You could calculate the G plus and G minus, the commutator, and find it to be ordered into pi S or minus S, depending on the S to be positive or negative. In this case, let's see. Now, you might.
I'm
Yeah,
sorry.
go ahead.
So the K of R is sort of like the Hamiltonian that generates boosts in all of R.
Yeah.
And K of A plus is the Hamiltonian that generates boosts in A plus.
No, sorry. No, sorry. K of R is just a boost. The Hamiltonian generates boost.
Yes. And what is K of A plus?
K of A plus is the modular flow of A plus, but we don't know what it is. It's actually not local.
I see.
It's that some sort of, it's kind of funny that we do know it's not local.
But suppose it was just a CFT in 2D CFT flat space, then K of A plus would not be just a modular flow of that. It would be.
It would be the conformal transformation that will have these two fixed points.
Okay.
Right, and just push this thing that way.
Okay.
So up to conformal transformation, in the case of vacuum, you could find it. But here, because of the fine temperature, that conformal symmetry is broken,
Right.
and this is not local.
Sorry, I thought that for null cuts of the horizon, the modular operator.
Yes, the action of this on operator localized here is local. That's why I get the PSL2R on the horizon only. Right? But the local Poincare algebra is in the bulk.
From the boundary point of view, it's very non.
Absolutely.
And intuitively, why is that positive, please?
Oh, it's there's no intuition for me of that. It's just one of the deepest results of modular theory. It just says that every time you have an algebra inside the large algebra, the logarithm of the density matrix of the larger one is as an operator smaller than the logarithm of the density matrix of the smaller one. Now I have to tell you how I compare them. That's the proper comparison by talking about the full modular.
I mean, in like very simple tensor factor, if you want intuition from like tensor factor.
I'm willing to do.
Yeah, it comes from monotonicity of relative energy. The fact that if you take a smaller something instead of bigger something, you're chasing stuff up, right? So the relative entropy decreases under that already. And you can show that up to some manipulations, ends up being this positivity.
Okay. I was thinking there's some time evolution. And I was hoping for some answer like you're evolving only part of it or something, whereas here you're evolving the full thing.
No, I don't think it's that simple as that.
Okay.
It's more complicated.
But it's certainly true, I think Nima should say, but it's certainly true that in factorized settings and stuff, you can derive this from monotonicity of relative.
I would say the following: the monotonicity of relative, well,
I know in the algebraic setting is more complicated, denser factorized settings.
No, yeah.
even in the sense. Oh, okay, sorry, go on.
Suppose I have two balls. I'm doing ADS-CFT, I take the boundary, I have two balls. The boundary, one is bigger than the other.
Yes, yes.
This is a situation where this should apply.
There's all, yeah,
Yes.
yeah.
Okay, now I can construct both of these cases geometrically
Yes.
in this situation.
In the vacuum, yes.
Yeah, just in the vacuum.
Yes.
Okay, then I should be able to just see it with my own.
Oh, yeah, it's a particular conformal generator. That's
Can you just translate that?
It's like a positivity of
Energy.
Positivity of energy.
Yes,
I think you've
yes.
seen this before. If you take like a diamond and like you deform the diamond a little bit. This difference is the anicosity.
This is the pie cut here.
No.
Yeah, fine.
It's the anicosity.
So that's true. So if you take chiral free fields, right? This is the modular flow of this is boost around this point. A larger region is boost around this point. If you subtract them, it's just translation in this direction, which is P minus is positive. So the conformal field theory examples of a circle inside a diamond, double coincide, that's a
So
generalization.
this I understand. In this case, this this quantity is a geometrical sort of action, which is manifestly positive, but
Yeah.
null energy there.
Yeah.
Now, surprisingly, lots of times, well, it's always positive.
Uh-huh.
And sometimes this positivity is not geometric, and that's what we're using here. And it still gives you this funny Lie algebraic structure, these groups, these algebras, I should say. But it's there, but it might not be space-time.
This requires some unitarity or something like that.
Oh, yeah, 100%.
Okay.
Yeah. I think it's monotonicity of relative.
Unfortunately, that doesn't.
It's a deep result. It's a very deep result.
The fact that if you look at smaller regions, you lose input.
Yeah.
That's all.
Yeah.
All right. All right, but is this?
Null energy conditions.
So then you conditions.
But that's how.
Actually, I do have a comment about null energy condition. Well, I'll get there. I'll get there. But here is this step. So you might, if you're very operator algebra oriented, you might ask me what the hell does this mean? These are unbounded operators. So this is just like heuristics. Of course, the theorem is about the algebra, the group generated by the exponentiated radians of these. That's so that they're bounded. So there's a proper way of doing it. Here are arguing for it heuristically, right?
So do I have to care about this last commutator?
Yes. Otherwise, you don't get a to the Poincare.
Okay.
Right? So this will become P plus and P minus. It's for 2D Poincare locally, it's essential that they commute. If this comes out to be minus 2KR, that's ADS2.
And this is exponentials.
Well, I'll actually give the example of ADS2. There is a case where it comes out to be ADS2.
Sorry, and that's minus positive number times S.
Minus,
So there's O in the O, what is the exponent?
oh, minus 4 pi S.
Minus 4 pi S. So is this S going towards making?
Yeah, I think, yeah, so I think
Other way.
if I'm going to minus, this should be plus.
Yeah.
Yes, correct, thank you. I had a minus plus, but yeah. So that's like zooming in here.
Yeah.
But remember that all I've said, just imagine in your head some sort of quantum mechanical system and an abstract net of algebras labeled by a bunch of arbitrary labels. All that you need to know is that whether there is future and past modular algebras. This could be super abstract. And once you have it, you could always draw these diagrams. It's not the space-time, but there are all sorts of the algebraic constructions. The PSL2R goes through as well. So there is a skeleton of a geometry there.
So now coming back, I suppose to this original, like the question that you asked at the beginning. Is the difference when there's a geometry and strong coupling, let's say the difference that is that these things are generated locally, like some integral or some stress tensor or something like that. Whereas if you move away from strong coupling, these are more abstract things, but perhaps not realized in it. So how should
away from the strong coupling, this structure gives you a generalization of the A-neck operator. This generalization does not match the generalization based on chaos, where people talk about the, what's it called, the operator, the Poincare. This is not that. As a matter of fact, yeah. And it's a very important question to answer, what is this generalization? Because why is that? Because with respect to this definition of a KR, if you calculate the Lyapunov exponents, it's always maximum. Whereas we think that, so you might wonder, how come that we expect that 1 over n corrections once you go to finite n, right? You don't have maximal chaos anymore. So your geometry should fall apart. But from the point of view of modular chaos, it's always maximum. Now, this generator is a generalization of the A-neck operator that to finite lambda, sorry, I said finite n, I misspoke over there, finite lambda, I meant. To finite lambda, which is not what we had considered before. So what is it? We don't know.
It's certainly not integral of like class.
Definitely not. Most definitely not.
In the geometric case, we should get an SL2R associated with every bulk. Now you're getting an SL2R just associated with the tip of the bend stack.
You mean the local Poincare?
Yeah.
Yeah. So so this was that was what we discussed in our paper. We generalized it a little bit, but we don't have an answer to what you just asked.
But maybe it's good, right? Maybe it's only a strong coupling that you get somehow.
Very, very good. Yes. Okay. I've thought about this a little bit. So yeah, there's a sense, if what Shiraz is saying is correct, which at the moment we have all reasons to believe that's the case. In these abstract algebraic setups that I was discussing, you only can see geometry in the vicinity here, right? Just like here. And then out there, whatever it is, we don't know what it is.
Yeah.
Right? So then it would be nice to understand how large coupling or large gap is making the geometry continue. But we don't know. Like, so my student Leung Lam, he generalized this result a little bit under some conditions. He could push further, but we don't have a full story at all.
And it would also be nice to go the other way. That is, start in a bulk, turn on string corrections, and somehow see that that things remain good there.
Yes,
but not so.
Absolutely. So this work I consider as like motivating a whole bunch of calculations. But unfortunately we haven't done the calculation. All that we're doing for now is just large cube SYK.
Somehow this edge.
Sorry.
Yeah.
So the edge seems insensitive to detail.
Yeah.
What do you have a feeling for why?
No, I do not. Now, actually, regarding that, another question that we have that well posed even at infinite n is, well, like I talked about zooming in here, right, to get local flat space. But if I just look at the corrections, I should get curvature. I should be able to read off curvature algebraically. This is actually something that was hinted at, like was discussed by Jan de Boer and Lampros and collaborators a while ago, but not using this in this language. So the curvature is definitely encoded there somehow in the strict n going to infinity limit. So it's less universal, of course, but.
How does coupling or n enter into this discussion?
And how does
I can see, yeah.
Yeah, n gives you n for us is a way of getting GFF, generalized fields, which gives you a violation of the time slice axiom.
Yeah.
I don't know if that's the only way, but that's the way for now.
Your mills or GS entering.
Does not enter. That's what's fascinating about
But
it.
somehow from area CFT it is GS times n.
So what I want to conclude is this. What I want to conclude is that holography gives us examples, large and large gap gives us examples where there's geometry everywhere, right? But using this an arguments that doesn't seem to rely on finite lambda, at least in an obvious way, we seem to be getting some sort of geometric structure away in the vicinity of the horizon. But how far does it go? We don't know. But I would also say that we see the PSL2R on the horizon, period, everywhere. That's not a local thing. That's just everywhere. So that I don't understand. at the moment.
Sorry, so PSL to R is on the horizon, and then what happens at the bifurcation point there? There is some, this commutator vanishes, is that the point?
No, I'll explain. I'll give the example to yourself right away.
No, so this commutator vanishes along the horizon, is that?
No. Let me work.
What last, sorry.
Yeah.
Similar to like how we see local bulk in multipolarity, because you're seeing the end of that, the light rays are moving. So it's like some high energy.
But it's sort of interesting in that situation, the Poincare singularity is smeared out by both finite n and finite lambda. But he doesn't seem to see that.
Wouldn't you say that it will, the region close to the bifurcation point will see the alpha and corrections?
I don't have, like, everything is just algebraic character. So it is possible, sorry, I have to stress this. It's possible that somehow it enters the discussion indirectly. That's why we have to work out examples. The algebraic characterization doesn't seem to care, but those words are just words until we work out examples.
Sorry, at the beginning of your talk, you talked about how a little local patch has this SF2. Can you see in what you're doing that you're focusing on a little local patch in any way? At the moment, I see that you're taking this S to go almost the whole thing.
Yes.
How do we know we're getting the physics of that little local patch?
Oh, do not. All I can say is that we know the action of, so we know certain things about it.
In the case that is geometrical, are we focusing on the local patch?
So yes. When this is very large, then you could use modular theory to show that in this region, the modular flows of these guys I said are not known, but they're almost loose.
Yeah, that's the usual. I mean, in geometry, that's the usual statement,
Yes.
right? But isn't this thing acting on the whole space, not just on that patch?
Very good. Yes, we don't know. The answer to your question is unknown. Yeah. So we're saying that there is this structured piece of like approximate local Poincare algebra acting on all operators, but we only see that physically here. We don't know.
So Nima, just,
Yes.
probably very basic, just to understand, so this D plus D minus C had some commutator, and you're saying that in order to get PSL to R, that should be zero?
No, PSL tour, I haven't, I'm gonna mention the
Okay,
PSL
so
tour.
what is this business with this?
That was a
commutator?
local Poincare algebra.
A local Poincare algebra, and then that vanishes in where exactly?
When you zoom in near the horizon, well,
S goes to minus infinity.
S goes to minus infinity. Zoom in here. So that shows us saying that now that is justifiable because in the vicinity or the action of these operators and the operator localized here, indeed, we could understand geometrically it's like almost boost, everything is fine. But we're making these statements about the commutator, these operators in the Hilbert space. So they act the same way on like crazy operators, non-local operators as well. We don't really know.
But in the case that it's geometrical,
Yes.
just n equals 4 angle strong coupling,
Yeah.
there you should be able to work the whole thing out explicitly and see what this SN2R is.
Correct.
But is it localized at that patch?
Well,
I-
in that
I-
case, from the bulk point of view, we know, right, like the P minus or P plus would be just T plus integrated, isn't that right? P plus P minus would be T, the plus.
Localized here
Yeah,
is,
yeah.
but away from that.
If we were in the middle,
It's a calculation that,
in
yeah,
the middle of the space.
In the middle.
yeah, it's a
Okay.
calculation that you could write down explicitly. People have tried to write down explicitly. But it's not.
But there's no isometry, right? There's no SL2R isometry in the whole space.
Correct. Well, I have to emphasize, it's not SL2R. It's a local Poincare algebra.
Sorry. No Poincare, sorry, local Poincare.
Yes.
There's no way.
And that's an unsolved problem. Okay, correct, absolutely. We don't see it.
I mean, you, in this geometric case, P minus and P plus are, you can write them down explicitly in the bulk, in terms of the bulk stress tensor. And then you can take an operator very, very close to the horizon, right? I suspect the action
There will be.
will be,
So what if you take an operator in the middle?
you can calculate.
No, sorry, so let me say that. That's KR minus KA plus
Yes,
is not translation everywhere. It's only translation here.
that's what I'm saying, you can write
Yeah.
it down as
So
integral.
if I look at the action of it here,
Yeah,
It's something crazy.
but it's almost free field theory, so you can, you can calculate this, right?
Well, we're doing a calculation, but yeah.
You can calculate, but there it maps to an isometry in the bulk. A local isometry.
Yes,
Here cannot, because there's no local isometry.
correct, absolutely,
No,
absolutely.
It's not crazy stuff.
Yes.
Absolutely,
So
absolutely.
it would be nice to know what,
Absolutely.
It's some like smearing of fine.
so is it something deep or something kinematic that you can do second to know? I mean, could I just do it all the time?
But even if I would say, so Shiraz, I would say it this way, even if it's kinematics, it's still surprising, so there's some information in it.
It's terribly surprising to me.
It's very surprising to me, so as I said, like, we seem to be, so these pictures we're drawing for non-holographic theories might be just like some way of representing some symmetries that exist in the theory, but a priori, the existence of these symmetries are all very shocking to me. And this one have nothing to do with space-time. That's still, I'm surprised that there are these symmetries. Now,
Sorry, just to understand, here your construction started with this subalgebra R of this full algebra, right?
no, that subalgebra A plus of R.
A plus.
A plus is the future algebra, future modular algebra of R. Because the modular flow of R is killing flow. It's geometric, so now it keeps pushing this up. In none of the setups that I've been discussing, so every time we say modular future algebra, the larger algebra is still subalgebra. Because if I take the whole thing, there is no modular flow.
But what I was going towards is that one can repeat this, I think. I mean, as I said earlier, I mean, can you not say this for even some smaller patch?
No, because the actual.
So what exactly is being used here?
That for R, the modular flow of that is killing flow, and we know that. But if you take any other region like this, the modular flow of this is not known.
Killing flow.
So the killing flow is, so it's U, this is V.
No, but I don't know any bulk, right? I just want to construct, there are some bunch of algebra that I want to construct automorphisms of.
Yeah.
So if I have this density matrix of any region,
Okay,
there is I can associate to this all these subalgebras that you're talking about, all these.
if you don't know any bulk, then the theorems speak for themselves, yes. But I'm just giving examples.
Yeah,
all the
so,
way to the
so
local.
in that case, one can again ask, right? For every tip where these two light cones meet in the bulk,
Yeah.
you seem to be having some algebra.
We cannot explain that.
Okay.
At the
So
moment,
in
we
that
cannot.
sense, it's not quite, that is some posterior understanding of radicity.
Yeah, we
But-
cannot
but
explain that.
Really just everywhere, right?
Yeah, it's everywhere, absolutely, you're absolutely right, it's everywhere.
Yeah, just-
We
just
cannot
see
explain
whether I
that,
understand.
100%. We cannot explain that at the moment. It might, yeah, I'm not giving up on the use of these tools. It's possible that like a fancier theorem or using the same thing will give it to you, but at the moment we don't have it. It might require newer physics, we don't know. Okay. But let me, yeah, okay, I said what I said. Good, so now the PSL to R. So far I was only talking about the local modular flow, local Poincare algebra.
You can turn on the recording if you.
I said what I said. Sounds like James Bond.
All right, so this is A, and I actually don't need the task of this thing. Okay, so this is, I'm gonna call R, and in this case, the relative commutant is, I'm gonna call N. If the theory is massless in the bulk, if I'm massless fields or CFD in the bulk, this algebra will be non-trivial. So I have a modular future algebra that is standard. Okay, good. So in this setup, what you,
Standard was what again?
that the relative commutant
that
is generates all. Now, what are the generators of this?
So that was used in all this so far?
No, that is for the PSL to R. If you want to say the word PS, you want to get PSL to R as an exact overview, so you need that. But previous discussion didn't use it because it was local.
Yeah.
Right? So here, the algebra is generated by the following. So the action of this is local, it's modular conjugation. is reflection. So you take n union n prime with respect to that, it gives you this algebra. Call that M. So this is M. Now, K of R, K of A, and K of M are the generators of PSO to R, L0, L1, L-1.
And there's some reason we should have expected a PSL to R?
Aaron Wall had some sort of a proof using quantization of free fields on a black hole background and using assumption of ultra locality to prove the actual existence of PSL2R. But there's a lot of physics that goes into that.
So SL2R requires an ADS2 somewhere? No.
Not necessarily.
Okay.
Not necessarily. But my next example will have an ADS2 in it. So, yeah, is this clear? It's this action of, it's just conformal field theory living on the horizon.
Conformal field theory on the horizon.
So how do conformal rise to an S2? What is it?
Sorry?
CFT on an S2?
No, this is just on a, it's like a Carl free field on a null line, right? This is CFT analog.
Every point is an S2? No.
I've already compactified.
Oh, you already compactified?
This is the S wave. Okay, I'm gonna come back to all the caveats. I'm intentionally talking about 2 dimensions. Some of this stuff, well, yeah. Good.
How to choose n prime? I mean, n prime is the same length as.
So the modular flow, this is geometric. This modular conjugation, which is another thing that's defined in modular theory, is reflection around this. So n prime is a reflection of n around this point. So n union n prime, this guy, and then which one? What else? This guy will generate pixel one. Now there is some sort of a nice intuition here I can try to provide. If I have AT plus B group, if I want to get the full PSL2R, all I need is inversion. If I have inversion, then I have, like special conformal transformation, just like inversion, translation, inversion. That inversion is provided by the map that swaps A with N. This whole structure, what it does for you is it just shows as the proof adds to the previous construction and Z2 symmetry. That's all it does, which is inversion. But once you add it to this, it becomes very powerful, it gives you PSL2R. It's a symmetry that swaps the algebra with the relative content.
This is some kind of modular conjugation.
Yeah, modular conjugation, a literal modular conjugation of M, take M. Now, there's a beautiful paper that is over the algebra people wrote that takes this construction. Of course, they were not thinking holography. They prove a whole bunch of theorems that go in the direction of reconstructing. So all of this was in 1+1. Like I'm going to S wave for all my discussions. But what they do is that they construct this whole program that if you just read it word by word, it seems like they're trying to reconstruct the conformal structure, the causal structure of the bulk completely. They actually claim that they can recover that completely. But we're trying to decode their papers. We're in the process of that. So that's it. At least this program, when I said that it gives you the Penrose diagram or like gives you some sort of skeleton of geometry, we seem to have the theorems. We just have to decode what these mathematicians have done. Let me give you another example of PSL2R, which might be interesting. For me, it was really, really interesting.
So I think basically,
Yeah, go ahead.
where exactly is the large being used?
And the fact that once you use, you map these bulk algebras to the boundary, right? You get a theory of GFF, right? That's from the point of view of the boundary theory, a realization, purely boundary realization that involves logic. Of course, in the bulk, these are just like normal quantum fields, but the magic of this is I'm saying that forget about the bulk geometry. I want to realize this abstractly and inclusion of a abstract net of algebras.
Yeah.
Large N allows me to do that, but I don't know if it's must. It's a way to do it, as we learned from Liu and Lufthansa, but it's not clear to me a priori. That's the only way.
And then for this Poincare group,
Same,
Poincare,
same.
etc.
I think
Well, you don't even use this N business there, right? I mean.
No, I use the large N again. This when I said there's an algebra here, at finite N, there are no future algebra. Because they're Poincare, the single trace operators don't form an algebra, they just.
you know it at one time, you know it all.
Yeah. Because yeah. The Hamiltonian will generate for you everything. You need to take a parameter to infinity, right? For all, and it's actually related to the fact that modular flow keeps decaying. Right, it's the same thing as, well, I don't know how much time I have, but I'll get to information loss maybe at some point.
Lunch cutoff is one.
All right. Okay, so let me give one more example of this and then I'll switch to information loss. The other example is ADS2. It's an example that I absolutely love. Because this PSL2R is acting on a 1D horizon, right? The other one is, I'm going to give the simpler example that we absolutely understand every aspect of it for now. But there are more complicated examples here. Take Poincare ADS2. Here's one algebra. I'm going to call this R. You could show that this is the future algebra. This is the past algebra. In the case that the GFF on the boundary has integer, so the spectral density of this guy has a delta. If that's integer, it means that in the bulk you have massless free fields. In that case, this is geometric. This is the future algebra, this is the past algebra. And we can actually show that the PSL2R you find is the ADS2 PSL2R. This generalizes to ADS2 Rindler and the cases where you don't have the, well, this is unrecorded, where I think it does, that we don't have integer delta, but instead of PSL2R, we seem to be getting a universal cover of PSL2R. Now, there are some details of those theorems that we're trying to work out right now.
If you have an ADS2 black hole, that is also locally.
ADS2 Rindler, yes.
Yeah, that's right.
Yeah. So that's the case that we're fighting because there are some subtleties regarding the theorems. We're trying to nail it. Yeah, but this is because this is an exact symmetry. It's at every point, right? Here, it's not just near something. It's every point. So ADS2 is ADS2.
And you have an identification of these in the SYK.
So Maldacena and collaborators worked out the generators of ADS2 in SYK. So
And it's all nearly ADS2 or just
yeah,
nearly?
yeah. So it's a question of scalings, right? Scaling limits, and we are trying to work this out. It's not done yet at all. Actually, there are people who are ahead of us in this. I think Matthew Donaldson. We started calculation at the same time, but he was much faster than my student. So I think he's gonna put out a paper soon. So he's beating us, I think. But that's what I understand.
This is something that can exact SYK or in the zero mode.
Large QSYK actually. That's the simplest setup where calculation could be done, and there's an SL2R.
Yeah,
it's known that
the bracket in terms of the rule will and that is
right. Right. Well, I yes,
Okay.
yes. Now there are comments about going away from large N, but I'll say that at the end. All right, so very good. So shall we talk a little bit about the hierarchy, ergodic hierarchy? Any questions here? So where do these conditions come from, like these future algebras and all that. I know that Shoy talked about the ergodic hierarchy, so I'll keep it quick, given that we don't have much time. I will just try to give some basic intuition. So these conditions I'm writing down are not just random. There's a long history of this. But in order to explain this ergodic hierarchy business, I'm going to give the example of a Hawking page phase transition because we're physicists. So the Hawking page phase transition is this setup where you start with, you take the thermal field double, the Hartle-Hawking state, right? So some that here E is from over E minus beta E over 2, E left, E right. And there's a phase transition below which what you have is two copies of thermal ADS, and above it you have thermal field double, the phase transition, right? Both of these are okay. We're gonna focus on the S wave, right? So here, even in this case, even though I drew it this way, it's on the S wave. So I'm gonna list a bunch of properties that we do know, we associate with the physics as the transition happens. Property number one is that below the transition, the field theory in the bulk here is it's a full Cauchy slice. So the algebra is type 1. It's just basic quantum mechanics, right? Whereas above it, as was argued by Liu and Muthauser, this algebra is the algebra of half of quantum, half of the Cauchy slice is type 3-1. So there's a type 3-1 algebra above there. Transition. Of course, this is all, and now one important property of type 3-1, if these words don't mean to you much, is the fact that these algebras have infinite entropy. They don't have finite entropy. Right? So somehow in the limit of n going to infinity, the entropy of these guys blows up.
Sorry, can you remind me what the ones do?
Well, I can tell you where it comes from, but let's have this conversation. Yeah. For the purpose of this conversation, algebras are either type 1 infinity or 3-1. The rest of them were not before that. So property number one. Sorry, I'll come back to that again. It's called strong mixing. Strong mixing is this Malvicina's information loss business that you take the 2-point function of left-right operators and you evolve them with time evolution. This is modular time, right? Because each copy is thermal. Modular Hamiltonian is just Hamiltonian. You look at the connect, I'm not going to write it. Connected correlator, gravity tells you that it decays forever, right? So the connected goes to 0. Connected correlator goes to 0. That's called strong mixing, right? Everything dissipates. Whereas at finite n from CFD with dynamics, you expect this to be just almost periodic. There's property 2, which is second law of thermodynamics. So gravitational systems have second law. There's a coarse grain above the Hawking page. These are all emerging above the Hawking page. So these are characterizations of phase transition, right? There's a second law of thermodynamics above it. Coarse grain functions, entropy functions grow monotonically in time. And that entropy function is definitely not the entropy of this region, because this is, as we said, it's type 3-1. That's infinite entropy, so you gotta be a little bit smarter. You have to do coarse graining. There's property 3 is the future and past algebras that emerge.
So please say what you said about second law again.
Second law is just a statement that, like, well, there's an entropic monotone that grows forever here above the transition. Second law
of the horizon.
Yeah, the second law of gravitational.
Yeah.
General entropy. Yes.
So that means that if you don't consider the full algebra, but you consider some part of the algebra, then you have this.
Yeah, you can imagine the language that I use is future algebra. Everything I can measure from now until strength.
No, but that you said the entropy is ill-defined for, right? If I took the full picture algebra, then it's
The entropy is still defined, but mutual information of regions, there's a way to make it work. But it's not just it's subtle, but it's not just, it's related to that, but it's not like.
But in the geometric case, you're really just talking about the increase of the area, or not?
Not really, because like it's hard to. No,
You're talking about generalizing.
I'm talking about generalized entropy.
Because, no, I'm talking, I mean, the difference is that quantum correction, like it's the.
I understand, but let's go to infinity.
Yes, then it's generalization of area. Yes.
But I mean, there's no.
There's no back reaction.
Yeah, no back reaction, right? So that's not a very useful statement.
I see. You're saying you're reading a very small fluctuation.
Yeah. Then that.
I see. So you're the entropy of the state. But do you have to take into account so you don't have to take into account the increase in area of the horizon? In what you're,
I mean,
is the second law normal GR second law or not?
When I say second law here, I mean normal GR second law.
Okay.
And also Aaron Wall's version, which is like the
Fine, sophistication.
Sophistication thereof. It's not conceptually deeper.
Right.
And why can't we make this argument before below the edge?
Which argument?
The second law?
Because there's no horizon area.
There's no horizon here.
No, but just, I mean, again, just the boundary operator motions of the future algebra, etc. Those should be valid at larger, right?
Yeah.
So there should be some inclusions.
Because it's like type 1.
Yeah, it's a
You know it.
Yeah, like
No,
there's no.
but larger, I said larger.
But
That
it
doesn't
matter.
matter.
Algebra is that economy.
Not every large N algebra has this. I'll actually say that, but like it's a question of spectral density.
But this is some state, right?
So take theory of generalized fields. You know that n going to infinity, these are all generalized fields, right? The generalized field is listed as in KMS, is finite temperature. So the only thing I need to give you to define the theory is the spectral density, the commutator, because the state is already fixed. Everything is fixed, right? So the commutator. Now, if the spectral density has certain properties, the algebra is type 3-1, otherwise it's type.
So when we say spectral density, this is some characterization of the state.
No, that's a characterization of the theory.
Of the theory?
Yeah.
No, but I thought these two scenarios are different in the state, right? That beta is above or below a certain value.
From the point of view of the boundary, the modes are different.
I think he's looking at small fluctuations around that background. So small fluctuations around just pure ADS look very different from small fluctuations.
So when we're talking about algebras, we are talking about the state and the operator algebras.
It's a
are
one-dimensional
the neighborhood of
correct.
that state.
So the state is the vacuum and all the excitation defined on top of that vacuum.
And the operators that you are looking at when you talk about algebras move you in the neighborhood of that state.
Of course. Well, because we have taken these yeah.
Oh, go ahead.
Now in these regimes of quantum field theory, there's not a neighborhood of it. These are different sectors of the theory. There's disjoint sectors of the theory. Yeah, but if you have finite temperature quantum field theory,
Yeah.
fluctuations will not change the temperature in infinite if you have infinite volume. So these are different sectors of the field.
I think we're looking at finite energy deformations of a given state.
Finite energy deformation, literally.
Big, not an energy
Yes.
deformation which is of the n square.
So
Yes.
all this algebra, all this discussion was in that sense.
Yeah, n goes to infinity, so all the fluctuations cannot increase energy by order n squared. Cannot back react. They cannot back react in the geometry. Yeah.
Okay.
There is property 4, which is exponential decay, polynomials, right? A dense set of operators decay exponentially fast. Not only the mix, their strong mixing, the connected correlative decay, but also they decay exponentially fast. Of course, not all operators can do that. That's a triviality, but the dense set of operators do that. Okay. This is just quasi-normal analysis. And number 5 is this local Poincare. All right. Very good. So there is something called quantum ergodic hierarchy. This is about how ergodic flow is. You define a bunch of algebras, there is some sort of unitary flow that transforms operators to each other, and you could ask about how ergodic things are. It turns out in the order, just 1 second, the order is like this. This implies this, implies this, implies this, implies this, implies this. So this is the weakest, that's the strongest. They have names. These are called Anosov systems, quantum Anosov systems. These are called quantum K systems. These are, what am I calling them? Well, I'm not calling them anything. These are the strong mixing systems and blah, blah, blah. All right. So there's an ergodic hierarchy. There's a beautiful story. This was discovered by mathematicians back in a while ago, right? Now, the statements of these theorems that we're discussing, part of the content is that in the case that dynamics is modular flow, the hierarchy collapses. These three are equivalent. Because I said future algebras implies local quantum. So that is the result. One way of understanding the result is that this hierarchy collapses.
In the case when what again, please?
That dynamics is modular flow. That was very crucial. Or you could say dynamics is generated by positive operator. Right? So the one way of summarizing is that this hierarchy collapses. So you would ask me, can we get the exponential decay? Yes, we can, but it doesn't quite give you the spectrum you want. We're working on that, but yeah. I think
mathematicians were studying this, the physics context of general.
these are, so there is a well-known study of the ergodic theory in physical system where you have Hamiltonian dynamics. So people would start with a phase space, right? And then there's a Poisson bracket. And you could ask if there's the algebra of observables or algebras of measurable functions and patches of a phase space. They have inclusions and all of that. People have studied ergodic theory. It nicely connects to this study of chaos. And there's geometry there, right? There's a space, phase space. But the quantum ergodic hierarchy, people try to say, okay, I'm just going to take the inclusion of algebras, some abstract inclusion of algebras, some abstract flow. What can I say? Then they invented an ergodic hierarchy. This is the closest they came up with. I want to say one thing, which is this is I should probably call this maximal Lyapunov exponent. Lyapunov exponent. So one interesting outcome of this is that for the modular flow and von Neumann algebras, Lyapunov exponents must be maximal. That's the statement that these Lie algebras appear. So it's not also clear to us exactly what goes on to get sub-maximal chaos. In this language, you have to talk about C-star algebras or some other flow, some other dynamics.
Nima,
Yeah,
just
sure.
restarting a discussion that Vijit was having. If you were on the boundary in this thermal ADS, and you took a little time band, then you increase the time band, you're increasing your data, right?
Yeah.
So why isn't that some sense of a second law? No, not in the backward case, though.
Sorry?
The thermal ADS case.
Well, because these are not, okay. It's a sub-algebra of observables.
Yes.
I don't know how to associate entropy to sub-algebra of observables. If I could answer that, then you're absolutely right. All the definitions we have are for sub-algebras. It doesn't mean that there's no way of characterizing that.
Okay.
Sub-algebra as opposed to what?
Subspace of observable.
Subspace.
Means that like I can measure sigma x and sigma y and the sums of it, but not sigma z. I can't multiply. If I can measure observable 1 and observable 2, I can't measure observable 1 to the power of a billion times over.
No, but for defining entropy, what is necessary?
Algebra.
And that is not what you have there. Is that what you're saying?
Yeah, if you just say in type 1s, the set of observables I can measure from now until tomorrow or until eternity, if the entropy is finite, is a substance. It's like doing physics with finite resources. If the OE gives me finite budget, or if I have finite amount of time, I can never measure a subalgebra.
Yeah. So people I think in chemistry,
Yeah.
find something called a K-body density matrix. or identical particles.
Yeah,
They say I want to find a given a pure state.
Yeah.
I want to find a density matrix which only evaluates K body orbit.
Yeah.
That of course doesn't form an algebra.
Yeah.
But some people try to associate an entropy with an
So,
object like that.
there is
Call
a,
it Dwight or something.
I'm not very familiar with that, but the standard route to this is Jane's. Jane's entropy. He says, if you give me measurement one, measurement two, like a bunch of observables, I'm gonna consider the class of all density matrices that are consistent with those measurements and maximize entropy in that class.
Okay.
This is Jane's entropy, right? It's a formal definition. It's very nice, and there's evidence that this could be related to holography as well. It might be simple entropy that Aaron Wall and friends have talked about. We're not ruling it out. Like, we're not saying that there's no second law over there. We're just saying that there's an obvious second law here that we seem to be obtaining. That we don't know the mathematics. We haven't solved anything on that side. Of course, a closed quantum system still has a second law. That's type one, and I think it's fine. Yeah.
You explain the hierarchy between this decay of two-point function and type 3 algebra.
Yes.
If you've been replacing type 3 by type 2 infinity, Newton constant, would that be demanding a particular deformation of the paper to something more realistic, regarding?
No. The one thing that's important to understand is that the type 2 infinity is not a brand new construction of the algebra. You say, I had my modular flow, I had all my operators, right? And modular flow was, with respect to this modular flow, my observables were all strong mixing. Hamiltonian, modular Hamiltonian was not part of the algebra. Of course, an operator, the operator itself never mixes, right? Because H2, H3, these are all conserved charges. It can never mix, right? So all you do from going from type 3 to type 2 infinity is just say, I'm now going to consider H. It doesn't change the story that all operators that are not Hamiltonian related with respect to Hamiltonian dynamics still mix, right? So now you just have this operator that you decide to include in your story, right? Of course, correlators of energy keep track of energy, so it will not. And that construction is perturbative in nature. It doesn't correct the, what we need to fix these issues is something non-perturbative. There's something fundamental non-perturbative, and that's going to type 1s.
How exactly are you defining the Lyapunov exponent?
Very good. Lyapunov exponent, but by that what I mean is the so thanks for asking that question. In this literature that predates this e to the power of I k t e to the power of minus I k t gives me the evolution of an operator O, and when people talk about the growth of this commutator, right? We have to talk about a matrix. It's an operator, right? We often in the story of O talk, so that the thing that grows is the size of this operator. This operator is growing. And because you don't want to look at just the 1-point functions of it, just square it and look at this guy, the behavior of this guy. Right? Now, in this community, in our community, the Lyapunov exponent is often associated to the behavior of this guy. Whereas in the quantum ergodic literature, it's just intrinsically about the growth of the commutators, which if you want to know how it behaves, it's about the commutators of operators. It's about the behavior of the commutators of operators. Having said that, let me just say one more thing. In all these discussions we're having, right? because n goes to infinity, everything decays away. So if you were to look at the spectral form factor, which is decays, comes back and plateaus, this just take in this regime, it just decays forever. Right? So in a sense, this is very, very early chaos, if you want to use those words. I put an asterisk next to chaos because these are all well-defined notions, but it's not quite chaos into the system like this. The chaos in this picture, chaos often has to do with the systems that expand, reach, fill the whole space available to them, start folding back, right? These are in limits that n goes to infinity, and it seems like there is no obvious chaos. That's a little misguided. I'm more than happy to tell you more about it, but that's the reason for asterisk chaos. Lyapunov exponent here is defined from the Lie algebra of the generators.
Can think of this approach to chaos, right? It's Lyapunov.
Yeah,
Yes,
people say early time chaos. People call it all sorts of different names.
Yeah, but even the OTOC measures, it doesn't really probe this very late time region where you have a plateau in the spectral form factor. It probes and earlier time scale.
But this is time scales of order inverse temperature. Right? It's not even like
I see.
scrambling.
I see.
It's not even scrambling, right? There's
So what
time-
is the precise definition? So you had a commutator where you got a 2 pi over n.
Yeah, so the generators of E plus and well, K I called it as they 2 pi say lambda or lambda plus minus lambda plus. So this was called Lyapunov exponent for a long time in this literature that predates our literature. Now people might argue which one is the right word, doesn't matter. The connection between this is not very, very well understood. Yeah, but this coefficient is also bound. There's a chaos bound. There's a chaos bound for this coefficient, so that's one reason to call it modular chaos. And if you want to know how you prove it, it's literally copy paste the proof of Stanford, Malison, and Schenker. It's just word by word.
So you could mod square this and look at that. O tau W. And get 2 lambda there.
Potential. I'm hesitant to say that because of some subtleties, but intuitively yes.
Okay.
Intuitively yes.
And just let me understand that. So you're saying that if I compute OTOCs with the Hamiltonian that is modular, this modular Hamiltonian, are you saying that that always has 2 pi as the exponent?
I don't want to say OTOCs, but what I want to say is that if you take modular flow, modular dynamics, and you look at the late time growth of or decay of commutators, with modular flow, and late time here is a regime where beta T over beta is large, but not comparable to any other parameter, then there is a coefficient that controls the decay.
But suppose I did actually compute the OTOC.
Yeah.
OTOC, but with time evolution by this modular operator. I go forward, back, and so on. Are you claiming that that will always give me the exponent 2 pi or 1 over 2 pi?
I do not know.
Would be surprising, right? I mean,
I do not know.
No, it will, right?
it will.
Because it's periodicity. And this 2 pi is the angle at the point where there is no symbol. I mean, I'm just taking the model of an interval, right? Some region.
Infinite. How?
Yeah.
Yeah. Okay, so that gives you the temperature. But why does it give you the chaos?
No, but the chaos exponent comes from the width of that strip.
But then a dynamically determined number also. In n equals 4 angles, it's not completely given by the temperature. Temperature times some function of lambda.
Because you need the bound, the same bound.
Yeah.
Yeah. No, I'm not sure about that. I'm not sure about that. All I can say is that this quantity, you can bound it using the same proof.
Yeah.
And for some reason, at least to my knowledge, people who discuss this were Tom Faulkner, Jan de Boer, and Lampress. They call this modular chaos. Hence, I put the asterisk I put next to chaos.
No, but it's like, where is it? Are you talking about something growing here? You're saying the size of this operator is growing, right? Or not? What is your definition?
Sorry. You're asking how is this coefficient related to decay or growth of the compound?
Right.
It's I
Just-
fully
just
agree with the
kind of-
argument this, but let me slowly build up towards it. So there is one connection which actually goes through Anatol systems. Let me tell you first how this controls the decay of the 2-point function. And the analysis is actually could be generalized, modulo some conditions. What you say is the following: you take an operator A. So I'm not talking about the decay of a dense set of observables. I'm gonna pick my operator A and B to be in the domain of k to the power of r, or just any positive number. Which is, I take an operator, I smooth it a little bit with respect to modular flow. One way of doing it is that take your operator and evolve it a little tiny bit modular time. To just make sure there are no contacts or no confusing things. But this is dense, right? I can do this arbitrarily small. Then you could prove from these behaviors that the decay of the, what can you prove? Oh, you can prove that the connected 2-point function decays exponentially fast. With an exponent that's controlled with r and lambda.
I thought chaos was about growth, not about decay.
Chaos is
This Lyapunov exponent gives a growth.
Of the commutator square.
Yeah.
But that's because it's a 1 minus something.
Mhm.
This is that one minus.
Whatever, then I'm saying you're looking just at the polynomial.
Yeah, that is what you're looking at 2-point functions, which is positive.
In this regime, the commutator is also decay.
So this is like a quasi-normal mode, is it?
It's polynomial physics. Yeah, it's polynomial physics. So it's very early time. It's very early time. So in that time scale of order 1, things just decay, including the commutator.
Right.
And this controls that.
But this has nothing to do with chaos. It's thermalization.
You could say those words. You could say those words. The origin of it, that this coefficient is also bounded by. That's perhaps one thing. But I would argue, well, okay, not being recorded, but I would argue that this is an early time notion of chaos that exists at strict infinite entropy.
But as Shreya said, we see this growth even at strictly large.
In the commutator square is like 1/n times e to the lambda t.
But
So
you
maybe
take-
to take the strict large and then it just gets you.
Let me divide, let me take a derivative of it.
Yeah.
Log derivative of something. Then I would strictly large n.
We cannot get 1 minus something. You can see.
Well, this is about connected 4-point function rather than 2-point function.
Yeah.
But in this regime, the connected ones also.
If this decay is rescued by plateaus and volcanoes, then people put it latent here.
Okay, so let me ask this question. I'm genuinely confused about this. In a system where I take my entropy to infinity, I don't think there's any growing commutator. Is there growing commutator in a system which is strictly the thermodynamic limit? I'm not aware of any such thing.
As Shreya said, I mean, you expect in reasonable states to start at 1 by n and then grow.
But what is n in this discussion?
Right, but suppose you take the commutator and take log derivative of it with respect to time. You will see that go with a lambda.
If you commutator square.
The thing that we do, the OTOC, we take that, we take log derivative. We take log of that and take derivative. That quantity, even at strictly large n, is a positive number, and that captures this growth rate. So it seems to me like we can make precise the statement that at large n, something grows.
I don't know, yeah, that's a very good question.
I think the point is that you see that the entropy is strictly infinite at n equal to infinity.
For sure.
Right. So,
Like, even putting autark aside,
yeah.
all the other definitions of chaos people discuss definitely must have finite entropy. I mean, ETH, all sorts of other different Hamiltonian. Because the corrections are always in random matrices are about exponentially small and interesting. Yeah, I'm genuinely confused about this, but what I'm confused about is the connection with the conventional literature and high-energy frequency. This literature, that's why I said I'm not sure if the word chaos is the right word for it, but this literature is self-contained with this set of definitions.
Right, so.
It's very clear
It's
what
just
it's
a different notion of chaos from the one related to UCs. But somehow the same bound, like the proof technique with the bounds.
That's kind of surprising that there's a bound. First of all, there's surprising that it's a bound.
A bound and thermalization.
Bound on thermal. Modular thermal.
People do try to talk about bounds on these thermalization timescales. The hydrodynamics literature, they try to introduce.
Viscosity.
Mhm.
It's sort of the other way, right? Because you can get viscosity very high. To make it small is difficult. Free carries have infinite viscosity.
Yeah, I think I'm not thinking the viscosity, but just this local thermalization timescale. There have been attempts to show that that also has an upper bound.
And that gravity will saturate it. Of course, anything will saturate.
I think this is pointing to a genuine notion of chaos in the infinite entropy limit in the following sense. So maybe the word chaos is misguided, but I think I can connect it to chaos literature more than just the fact that there's a similar proof. So if you have an infinite entropy system, like let's say a boost setup, right? The connected 2-point functions decay because the proper distance decays forever. And the issue is that there's no large parameter or small parameter to play, right? Now let's try to play the following games. This doesn't have any sub-algebras. Let's pick a sub-algebra which splits with respect to that. Now, let's look at the evolution of this sub-algebra with this modular rule. Now what happens is that the object of interest becomes, if this is A and this is B, this. This object is very interesting in many ways. First of all, delta of B to the power of quarter, delta of A to the power of minus quarter is conjectured to be trace class in many quantum field theories. Conformal field theories, as a matter of fact, is trace class. So that means that there is some sort of finite dimensional system you've defined in this infinite entropy system. So what does this have to do with Hamiltonian? Let me try to relate this to Hamiltonian. Take the limit where this is half space to this side and this is half space to that side. If you calculate this object, this is just this e to the power of minus some number Hamiltonian in class space. So even though in quantum field theory we have these infinite entropy systems, the way an infinite entropy system algebra sits inside the larger infinite entropy system, that I don't want to use the word index because that's improper, can still carry a finite entropy thing. And here the role of infinite or large parameter is played by, say, epsilon. This is actually, if you look at the literature of Faulkner, this is one of the reasons he actually called this modular chaos, because this object is all over this. And it's trace class actually. But okay, sorry, this is way off. So, but this is not quite the chaos that we're familiar with, but it's a genuine notion, I think it's a genuine notion of chaos in the strict thermodynamic logic. And it remains mysterious to me how it relates to the other notions. Yeah, thank you. All right, I don't have for today.
It was great. It was really great. Thank you so much.
So a few more questions if there are any.
Instead of considering just time bands where t is greater than some constant, could you imagine doing like floppy time bands where
Oh,
t is
yeah.
greater than some function?
Yeah.
And that could presumably give you a much larger, does that give you a larger set of generators where you can use, which you can use to localize enough points?
So on the boundary, you were saying?
Yeah, I was thinking instead of having t greater than t naught, say t greater than t naught of x, something like right here.
Let me, yeah,
I was hoping to get more information about it.
And you go all over the sphere? Possible. T greater than T naught of x is a spatial one.
Spatial.
And then.
let me give you.
Particular.
Let me give it a partial, the way I think about it, which is yes, I think.
Okay.
But I'm not, it takes certain assumptions I'm not willing to necessarily make. Take a horizon. Right? Here is a weird cut, right? This is the proof of ANEC, right? Which requires some sort of ultra locality, that the Hilbert spaces here are tensor products of each other. If you allow me to do that, yes, I can do that. I can get a much larger group. I can actually, Cassini has argued.
No, but the question is, does that map on the boundary side to like these floppy time? I mean, I mean, from the bulk point of view, of course, but how do I get it from the boundary?
Oh, why can't I play a game like this? Take radius 3. Right? Now I can take this and split it into, how do I want to do this? Well, that's a very good question. So I have not thought much about it.
You can talk.
But in the bulk, there's certainly this.
Yes.
On the horizon, there's this infinite dimensional group, which is a mystery whether it was what's going on with this. That could be centrally extended.
Those generators roughly correspond to having bulk subregions, which are like deformations of the, of the macro horizon.
Right.
So I was wondering whether there are some natural boundary subregions which capture these. It sounds like there should. Okay, we
Yeah.
More questions? Not, let's thank you again.